system that consists of a continuous stirred tank reactor right in the center of the screen. There's reactants, I suppose, flowing in from the left and products flowing out to the right. Now, I don't know if there's a chemical reaction. The purpose of this tank is really just to control the temperature of the liquid so that the outflow on the right has the appropriate temperature. Now, you notice in the upper right-hand corner there is a graph that shows the current actual temperature coming out of the tank. And you can see a slider here we can move around to change the desired output temperature, in other words, the set point. Nothing's actually changing in the process as I move this slider around. The only thing that's happening is my target temperature is changing. Of course, I can type a temperature in to the box below as well and set the temperature set point to whatever I want. Now, the only way to get the stuff in the tank to heat up is to apply more power into the power amplifier that then operates the heater resistor in the tank, whatever it may be, the heater coil. And that control is over here with the U0 signal. So I'm going to type in 60%, and you'll notice that the actual output temperature of the tank went from about 48 degrees or so, maybe a little more, to about 55 and a quarter or 54 and a quarter degrees or so, maybe a little more. But of course it's leveled off because I'm putting more signal into the control variable, or I've taken the control variable from 50% to 60%. I could take it below. I could put 40% in here, and now there's less power going into the heater than when I first began, and the actual output temperature of the tank, you can see over here on the right, comes out to 43 degrees or so, something like that. Now my goal is to find appropriate gains for a PID controller. One way to do that is to take the system to the edge of instability, as is recommended by Ziegler Nichols. Now, if this was an extremely dangerous process, this could be, if this heating tank was a dangerous process, the act of taking it to the edge of instability could itself be dangerous. But the way to do it, according to Ziegler Nichols, is to turn off the integral and derivative gains. Now, the integral or the derivative gain, right now none of it's on because we're in manual mode over here with the switch on the left. We're not in automatic. But I'm going to turn it into automatic mode. But before I do that, I want to set up a proportional only controller. So I'm going to turn the derivative gain to 0. That turns off the derivative action. And I'm going to change TI so that it turns off the integral action. Now, remember in the control equation, TI is in the denominator. So I need to set it to something really high, like 10,000 or something. Now, it turns out, because this is a mathematical simulation, we can actually type INF for infinite. And essentially what that'll do is 1 over infinity will go to 0, or is 0 if you want to call it that. We're engineers here, not mathematicians. So we'll call that 0. Essentially, all we want to do is turn off the integral and derivative action. And I've done that now. Well, technically proportional action's off too because I'm not in automatic mode. Now at this point, most students will go into automatic mode and try to measure the system's ultimate gain in period, but that's a mistake. One of the things that students often forget is you've got to drive the set point to the process variable. And you might say, well, if I can do that manually, I mean, after all, 50% is getting me pretty close. Probably, what is it, 51.2%, I think, something like that. If I can drive the process variable to the set point by myself, why do I need a controller? Why wouldn't I just set it and forget it? Well, because it's open loop control. Let me show you what I mean. I think it's actually maybe 51.5. Yeah, that's closer, but not quite. Maybe I don't remember my numbers. Let's try 52. 52 is better. It must be 52.5. I've just forgotten. So the problem with open loop control is that disturbances come along. Things happen where this is no longer the correct setting for the process variable to achieve the set point. Right now it's perfect. There's no error. We want 50 degrees out of the tank. We're getting 50 degrees out of the tank. But what if the incoming stream drops a little bit? Say it goes to 18 degrees instead of 20 degrees Celsius. Look what happens to the output temperature. It's now dropped to 48 degrees because we aren't put enough power into the tank to make up for that amount of heat addition or that thermal energy that's needed in order to finally bring this output temperature back up to where it needs to be. So let me move that back to 20. So I need an automatic controller. In order to get an automatic controller, I've got to get good gains. In order to get good gains, I've got to measure the system. So what I'm trying to do right now is measure the system. So let's put the system into automatic mode. You'll notice nothing happens. We've got a proportional only control, and remember that proportional gain responds to the magnitude of error. Right now there is no error. The error is exactly 0, so this 6.7 multiplied by 0 is still 0, so there's no change in the control variable from the 52.5% that I set. And you'll notice that in the chart on the lower right, 52.5% is the current value of the control variable. It's the amount needed, so the power amplifier is giving us just the right amount of power into the heater coil so that the temperature comes out at exactly the desired temperature. Now, if a disturbance comes along, let's say this drops down to 15 degrees, what happens? Well, we notice that, let me pause this, I'm going to hit stop actually. We notice that the output temperature dropped. It dropped to 49 degrees or so, which is not bad, but let me zoom in on it so you can see what has happened. Let's take this axis down to 45, take this one up to 55, just so that we start zooming in, maybe 51, and 48 or so. I'm just double clicking on these to change them. Look at what we see. I'm going to change the time, 41:25, so we end up right about there. Yeah, that didn't work. I was hoping it would zoom in. I guess I'd have to do that while it was running. But you notice that what has happened is we went from 20 degrees down to 15 degrees, and the temperature output from the tank started dropping like crazy, but it rebounded. Why did it rebound? Well, because now that there's some error, some difference between the desired value, the set point of 50 degrees, and the actual output tank temperature, you notice the control variable responded. That was the proportional control. Let's look at the control variable. 60%, that's probably a little low. Let's try 65%. There we go. And on the bottom we'll look at, let's see, 45, maybe 55 or so is 50. So you can see what the control variable has done, right? The error is non-zero, and so the error multiplied by the proportional gain gives us some change in the control variable. And finally we come to this sort of happy medium where, yeah, the process variable is not at the set point, right? It's at 49 degrees, not the 50 we want, but that gives us roughly 1 degree of error multiplied by 6.7%, gives us a response that gets us closer. It's not as far away as it was initially, but it's not at the set point. So it's sort of leveled out. Now this is the problem with proportional only control, that you can't actually achieve the set point. There's some steady state offset error in the presence of a disturbance like this 15 degree inlet temperature instead of what we originally had, which was 20 degrees. Basically this 52.5% we started with is not enough, but proportional only control can't add enough to actually bring the process variable, the actual output temperature, back to our set point. If it did, there'd be zero error and we'd go back to 52.5%. We're not trying to actually control the process right now, we're trying to measure it. So what we're really interested in is the dynamic behavior of the process. We notice that the oscillations, we did manage to generate some oscillations, but they died out. Now I'm going to reset the entire thing, and it's good practice to do that with these simulators because they can tend to be a little buggy if you don't. So let's see, let me change back to our original values so we can see everything, and let's hit play. So let's see, we're at 59.4, the magic number was 52.5, and what we want to do is get a large enough proportional gain so that the system will continuously oscillate. Now you'll notice that I'm first of all letting the system settle out. I want to start from a point where the process variable is at the set point. And 6.7 wasn't enough. I'm going to try 10 on my process proportional gain. And then I have to somehow introduce a disturbance so the system starts to ring. It starts to oscillate. I can do that by bumping the set point, which I'll probably do. So notice I take it up to some value and then take it back down. Not too crazy. But what I really want to get is nice, even oscillation around the set point. You can see that it's oscillating well. You can see that the control variable started out with large amplitude and is decreasing in amplitude. In fact, it looks like these are going to die out, so I'm going to crank up my proportional gain And notice I still have some oscillation. That oscillation is now growing. So now I'm going to go down to 11 or so. Now what's happening at this point is called banging the control limits. What that means is that the control variable is going between its maximum and minimum value. You don't want that when you're measuring the size of a system, when you're trying to find the ultimate gain. I'm going to back down to 10, see if the system, sure enough, yeah, it starts to decay. I'm looking at the control variable. Bump up to 11 when I've got good control variable variation. When I go to 11, it's too much. It starts to grow. So I'll go back to 10. I'm going to try 10.5, just bisect the range. There we go. Let's let that go for a little while. And it looks like the control variable did hit the upper limit right at about, what, 740, 50 seconds? Well, maybe a little less. Maybe 735, 740. But now it's hitting the limit. So 10.5 is too large, so my ultimate gain is somewhere between 10 and 10.5. So I'm going to go back to 10, let the oscillations die out. You'll notice that they're pretty small oscillations in the process variable, but in the control variable you can still see significant oscillations. So now I'm at 10.2. That's not 10.5. They look pretty steady, but it kind of looks like they're dying out. Hard to say, so I'm going to let it go for a little while. Remember, our time scale is in minutes here, so this is quite a bit of time. They are in fact dying out. I'll go to 10.3. Now the oscillations are so small, I'm not comfortable saying that I'm getting a good measurement of the system's behavior at this point. So what I'm going to do is purposely go to 11 just temporarily. Notice I don't have to bump the set point or do anything to get it to ring. It's already ringing. And then go back to 10.3 when I've got good control variable oscillation. And let's just see how that lasts. So 10.3, may have forgotten where I'm at. Notice I've got good symmetrical oscillation around the set point. At least it looks like it. I should probably zoom in a bit. When you start changing the numbers in the simulators, things start to kind of slide around a little bit, and sometimes you don't have good uniform oscillation. Let's have a look at this. Let's zoom in. 60. Yeah, it looks like we've got decent oscillation, but it looks like they're dying out. So somewhere between 10.3 and 10.5, I'm going to try 10.4. You can chase your tail with this all day long. Notice on the x-axis it goes from 1400 to 1600 minutes. That's 200 minutes. 200 minutes is what? Over 2 hours or over 3 hours? So I would say 10.4 is absolutely acceptable as the ultimate gain. Now I'd like to see how long it is between the oscillations. So what I'm going to do is zoom in. I'm going to grab the left hand number. I'm going to wait until the red line goes past the halfway mark. Then I'm just going to type in the number at the halfway mark, which is 1700. Now I'm waiting to press enter. The red mark is passed, or the red line is passed, so I press enter. Now you see we zoom in a bit. I've got to hurry, 1750, there we go. If you wait too long to type in a number here, the cursor will come back around and you'll have to try again. So let's see, 1820 looks pretty decent. There we go. Looks like we're getting pretty good oscillation. There's some noise in it or some distortion. I'm not sure why. Don't know that it matters. Anyway, I'm going to go ahead and stop the simulation now. And so now all I'm going to do is look at the range. It's from, let's see, 1910 to 1880. That difference is what? 20 plus 10 is 30. So we've got 30 minutes worth of time here. If I go from the very first point at 1880 and count the number of peaks, let's see, we got another similar point at about, 1885, 86, something like that, 87. There's one peak, 2, 3. Looks like we'd accomplish about 4 cycles, maybe a little more, but 4 cycles in 30 minutes. So if I grab a calculator, how long is it per cycle? In other words, what is the period of one cycle? Well, we got 4 cycles divided by 30 minutes. Looks like the period's about 0.133 minutes. Now it's important to remember the units, because 0.133 minutes, did I do that right? Let's see. Yeah, something's wrong. No, I need minutes per cycle, not the other way around. Let me try again. 30 minutes divided by 4 is 7.5 minutes per oscillation. So 7.5 minutes, you got to be really careful here. Notice the x-axis is in minutes, but our gains, TI/TD, are in seconds. So we have to be really careful here. So what we'd want to do now is select the gain based on the ultimate period and ultimate gain that we've measured so far. So at this point, Ku is equal to 10.4, and students get confused about this because they say, well, isn't that Kp? Well, it's the gain that I've used to get continuous oscillation, but this is it's more a measure of the system than it is a number that goes into a PID controller. This is not a PID controller right now. This is a proportional only controller. I remember the Ziegler-Nichols tuning equations told us to divide the ultimate gain by a certain number. If it was, what was it, 2 if we wanted a proportional only controller? So if I wanted to leave it this way and get okay control with a proportional only controller, I would take 10.4 divided by 2 is 5.2 and plug that in as my proportional gain and be done. But if I wanted a full PID, then I think the divisor for Kp, don't hold me to it, I think it was 2.2. So if we take 10.4 divided by 2.2, then I would need a gain here of 4.72. Okay. Now where you get into trouble is with the units on Ti and Td. Now I'm operating off of memory here. I'm pretty sure that for a PID controller we need Ti divided by 1.2, and then Td was ultimate period divided by 8. I don't remember. I don't have it in front of me. Let's just say that's the numbers. You can look it up on the slides. So if I wanted you know what? I know that Ti is right at about 252, and Td is right at about 63. Let's see how close I get. If I take the ultimate period, which was 7.5 minutes, now be careful, I need seconds on my units, so times 60 is 450 seconds for my ultimate period. If I take that and divide it by 2, which actually I think about 2 or so was the number for a full PID, then I get 225 seconds for Ti. And I'm pretty sure it was 8 for Td, so if I take the original, 7.5 minutes times 60 seconds, 450 seconds, divided by 8, then that is 56 seconds or so for the Td value. Now notice I've gotten numbers that are close to the original PID numbers that were in this simulator, and they are tuned values. They are proper values. I think the key difference is that when I calculated the period, I probably underestimated it by a little bit. I think the period's actually a little bit longer than 7.5 minutes. But now, if I reset my simulator, let's remember 4.7, 225, and 56. If I completely reinitialize everything, which is, again, good practice, what was that? 4.7, 56, and 225, I think. Put it into automatic mode, turn it on. Then I should have so-called good response, or Ziegler-Nichols tuned response. So now let's see how the system behaves in response to a disturbance. So the incoming temperature was 20 degrees. We're going to crank it down to 15. What happens? Well, the temperature did dip a bit there, but you see that the system recovered very rapidly and quickly found a new steady state value for the control variable that gives us the desired output temperature. Notice there's not this continuous oscillation. There wasn't tremendous overshoot. It was not bad at all. You might say, well, it did dip down a little, yeah, but the overshoot's on the other side. So this is pretty doggone good control. If we change our set point, let's say to 55 degrees, how does it respond? Well, you can see some overshoot there, and what I'll do is zoom in and then try to pause this. Well, that didn't work. I'll pause and see if I can. I don't think I could zoom in, but you see some overshoot, and then if you can see it, I hope the resolution's high enough. There's just very little undershoot. There's that quarter wave response that the math gives us, right? Once you've got the ultimate gain, ultimate period, you do the math, plug in Kp, Ti, Td, and now you've got good response, no oscillation, not too much overshoot, and quick decay in the oscillations. Now the Ziegler-Nichols method is not the only method for measuring the system. Let's reinitialize everything and start again. The other method is the Ostrom-Haugland relay tuning method. So what we need to know is what the system can accomplish. So let me turn the system on. Let's hit play. Make it full screen again. And so now the system's on. Let's see, we've got all of our default settings. We've got 70% as our setting. Let's go down to 0. What is the minimum temperature that the thing outputs? So let's see, 40% will go down to 0. It makes sense, it goes down to 20. Okay, fine. What about if we were to put maximum power into the system? What temperature would it achieve then? Oh, that's not what I meant to do. I changed the set point range, but that's okay. Alright, so it looks like it goes up to about 77 degrees or so. So our minimum is 20, our maximum is about 77 degrees. Okay. So now let's use Ostrom-Hagelin relay tuning in order to measure the system and then tune it. So what we have to do is select some amplitude of variation. Now the on-off controller is built into this control panel. I just have to flip the switch on the control panel to the right so that these PID gains are not in play and rather the on-off controller is in play. But just like before, what I have to do is find the nominal control signal manually. And what was it, 52.5 I think, with nominal settings? Yeah, so 52.5% gives me the ideal setting so that the tank produces a 50-degree output. That's exactly what I want. Now, with a 10% amplitude, what the controller is going to do once I put it in automatic mode, in fact I'll do it and talk through it, is go between 62.5% and 42.5%, because of course the control variable has a maximum of 100% and a minimum of 0% for its output. So 10% plus and 10% minus of that entire range is plus 10% overall, 40 or 62.5, and then minus 10% off 52.5 is 42.5. So right now the control variable is varying from the on state to the off state and vice versa. And you'll notice that the system is not really varying its temperature very much at all. You might be able to argue in some scenarios that this is actually pretty doggone good control. If I really zoom in, there's really not that much variation in temperature. It looks like it goes between, a little bit maybe below 49 degrees, a little bit above 51 degrees. Your thermostat in your house probably doesn't do this good. So this is not bad control, this is decent, but our goal is not control right now. We're trying to measure the system's response. So let me zoom in. You can zoom in on the process variable if you want, that's what I'll do. You could zoom in on the, why is it not zooming in? Not doing something right. You can zoom in on the control variable if you want when you're trying to get the ultimate gain, ultimate period. I'm going to zoom in on the control variable because zooming in on the process variable is not really working well for me. I don't know what I'm doing wrong. But let's see, red line over the halfway mark, go to 1300. There we go. Now I can see the control variable much better. 1350. I'll just go one more. Yeah, that's pretty good. And then I will stop the simulation. Alright, so now what I can do is measure the amplitude A of the control variable, but that's easy because I put it in. It's 10%. Notice I'm going above and below 52.5% by plus 10%, minus 10%. So that makes sense. But what about the error, the response? Well, it looks like it varies just a bit, but it's really not too bad. Let me see if I can zoom in some more even though it's not running. Yeah, it looks like that works. 51.5%. There we go. This is looking pretty good. 48.5%. There we go. So it looks like the temperature varies between, about 48.5% and 51.5%. But I need that, degrees, pardon me. But I need that as a percentage of the range. Now, you might be tempted to say, well, the system can go anywhere from 20 degrees up to 77 degrees. There's the range. Actually, it's not quite that simple. It has more to do with the signal going into the temperature controller from the temperature transmitter than what the system can actually detect. So these show measurement range and show scaling range, these are important, but I'm going to have to turn it back on to do that. There we go. So now they're shown. I can stop again. Oh rats, I've messed up my entire experiment because I forgot to count the number of pulses. So let's just run the experiment again. And let's see, let's zoom in. I think I zoomed in twice and had a pretty decent view of the control variable. Right now it's set up exactly as I wanted for the measurement. I think I'll go to 160 this time. There we go. And then I'll stop the simulator. That's pretty good. Now, this measurement range and scaling range of the temperature set point, these are important. They need to match, because what this is doing is scaling the signal from the set point so that it's not a temperature in degrees Celsius, but now it's a percentage, and scaling the signal from the actual measurement of the tank so that it's not a temperature, it's a percentage, because the controllers all need to work with a percentage range. They don't work actually with the temperatures themselves. So they're scaled the same way so that a temperature of 0 degrees will come in as a 0% signal, and a temperature of 100 degrees comes in as 100% signal. This can be a little confusing at first because the numbers match a little too well. But basically what that means is that if I'm getting a signal of 48.5 degrees Celsius and 51.5 degrees Celsius, then the temperature transmitter is giving me a signal minimum 48.5% and maximum 51.5%, which makes the math pretty easy, because to get the error response I need the difference between 50% and 51.5%, which is 1.5%. So because this is set up so nicely with these scalings set so that 0% is 0 degrees Celsius and 100% is 100 degrees Celsius, it makes our life very, very easy. So remember the Ostrom-Haugland equation for getting the ultimate gain from this measurement was to take 4 over pi times E over A, or was it A over E? It was A over E. So we need 4 times the control variable oscillation, which was 10%, so 0.1, divided by pi, and also in the denominator is the error response. Okay, so that's 1.5%. So since I put in 0.1 as 10%, I'm going to have to put in 0.015 as the percentage value in decimal format. So when I hit enter, that gives me 8.5 or so as the ultimate gain. Now remember, with the Ziegler-Nichols method, I got an ultimate gain of about 10.3 or so. And you might say, well, there's a difference there. Yeah, there's a difference. Controller tuning is often not, I don't want to say it's not precise, but it gets you in the ballpark. And so often it won't matter that the ultimate gain we've gotten here is not exactly right. If you were to just go in blind to this scenario, you'd have no idea whether your ultimate gain was going to end up being 0.01, 0.1, 1, 10, 100. You wouldn't even know the order of magnitude, right? There's this entire range that you could traverse before you even get close. So relatively, 8.5 and 10.3 are relatively close to one another. They're reasonable numbers and reasonable measures of this system. So if I take about 8.5, it's actually 8.48, but 8.5, close enough, and I want a PID controller, then I would need to divide that by, I think it was 2.2, I believe. So 3.8. I'm going from memory on the tuning rules themselves, but the ultimate gain then, being about 8.4 or 8.5, suggests I need about 3.9 for the proportional gain, and then I just get the ultimate period off of the control variable or off of the response. So it looks like we've got, let's see, what, 1, 2, 3, 4.5 or so cycles. So 4.5 cycles in a time of, let's see, 160, 200. The difference there is 40 minutes. And I've again done it backwards because I need 40 minutes divided by 4.5 cycles. That's about 8.9 or so minutes per cycle. Remember, I have to convert that into seconds, so times 60 gives me 533 seconds, which when I divide by 2 or so gives me a integral time of 267 seconds. If I then take the original number of 533.3 divided by 8 to get the derivative time, that's about 67 seconds or so. And so now if I go to PID control and hit play, make this full screen again, now I've got a PID controller that has been tuned with Ostrom-Haugland relay tuning, and then the equations I've used are Ziegler-Nichols equations for taking the ultimate gain and period and converting those into proportional gain, integral time, and derivative time. And so let's test and see how well this works. We'll change the set point to 55 degrees. I should change my scale here so we can see it. And it looks like we got pretty doggone good response there. You can see a little bit of overshoot, but quickly the process variable is driven to the set point. Let's change the disturbance input, 15 degrees on the input temperature. There's a little bit of dip, a little bit of overshoot, but not much at all. So this is actually good control, just like we got with the Ziegler-Nichols tuning. So you got to understand there's two parts to this. There's the measurement part, where you perturb the system and let it oscillate and see how it oscillates, and you get a measure of ultimate gain and ultimate period. You can do that either with Ziegler-Nichols or Ostrom-Hagelin. And then there's the part where you take the measurement, the ultimate gain and period, and you calculate the appropriate values of the proportional gain, the integral time, and the derivative time, and then you implement those in a PID controller, and you should have good response if you have a good measurement of the system.